Hi everyone, today I'm going to give you a full tutorial on how to make an EMG sensor circuit. You can use this circuit in order to control any electronic device. For example, you can use it in order to play a video game without using a joystick, a gamepad or a mouse. Here I connected my circuit to my gamepad so that I can make Robocop shoot when I close my hand. Of course, we will need several circuits like this in order to make him walk and jump, but this is just a prototype that illustrates the possible applications. I'm going to give you the circuit diagram and the PCB layout, but as a physics professor, I am against giving a ready-to-use solution without a word of explanation. So I'm going to go through all the details and calculations. Before that, let us take a look at the block diagram in order to have a global view of what is going on. The picture up there shows my muscle. Well, I haven't exercised lately, so I lost a little bit. Anyway. My muscle is connected with surface electrodes to a difference amplifier that amplifies the potential difference between two different locations. Then the signal goes through a high-pass filter in order to remove the DC component. We have to remove it because otherwise the signal would saturate when we amplify it further, and the circuit wouldn't be able to tell the difference between when the muscle is contracted and when it is not. The remaining signal goes through a full-wave rectifier and a low-pass filter in order to convert it into a DC signal. The signal is then amplified again in order to reach a voltage that is large enough in order to communicate with electronic devices. And optionally, an offset can be added to the signal in order to ensure its compatibility with the electronic device that you want to control. The EMG sensor circuit makes use of 8 operational amplifiers, so if you are not familiar with the OpAmps or if you need a reminder about them, check out my tutorial. You will find the link for the tutorial in the description of this video. So I assume here that you are familiar with OpAmps. Let us start with the difference amplifier. It has two input potentials, VEMG1 and VEMG2, that come from the surface electrodes connected to the muscle. One of the electrodes, it doesn't matter which one, is connected in the middle of the muscle, the other is connected at the end of the muscle. What needs to be measured is the potential difference between the two electrodes, so in principle it doesn't matter what the reference potential is. However, OpAmps can measure the difference between two potentials only if their values lie between the negative and the positive potentials of the power supply. This is why a third grounded electrode is needed, which serves as the reference for potentials. This electrode can be placed anywhere on the skin as long as it is not in contact with the muscle from which you want to record the activity. The OpAmp here works in the linear regime, which implies that the potentials at the inverting and the non-inverting inputs Vin minus and Vin plus are equal. Once again, if you don't know where this statement comes from, check out my tutorial on OpAmps. The potential at the non-inverting input Vin plus is easily determined by noticing that the resistors R1 and R2 form a voltage divider that has one side grounded. Now, for the inverting input Vin minus, the resistors R3 and R4 also form a voltage divider. but it is not grounded, so the formula needs to be generalized. This is easily done by proceeding as follows. Suppose that V hat was 0. Then the divider would be grounded and V in minus would be given by R4 over R3 plus R4 VEMG2. If instead it was VEMG2 that was grounded, then V in minus would be given by R3 over R3 plus R4 times V out. So, for the general case, we apply the superposition principle by adding the two cases. This is valid because resistors are linear components. Now, as mentioned earlier, the inverting and the non-inverting inputs have the same potentials, so we can solve for V out and obtain this complicated expression. But V out simplifies greatly if we choose the resistors such that R3 equals R1 and R4 equals R2. Then V out is a constant multiple of the potential difference between the two inputs. That's why we call this circuit a difference amplifier. Now, because the voltage recorded on the skin is very small, we need to amplify it. So here we are going to multiply it by 100. All we have to do is to choose R3 equals R1 equals 10 kilo ohms and R4 equals R2 equals 1 mega ohms. The signal is still very weak, but we cannot amplify it further yet. The reason is that it contains a DC component that is due to the fact that there exists a constant potential difference between the points in the muscle. So if we amplify the signal, it will saturate and we won't see any difference between when the muscle is contracted and when it is not. So we use here a high-pass filter in order to remove the DC component. For our analysis of this filter, we start by noticing that the inverting input is virtually grounded, so V in minus equals 0. Once again, check my tutorial on OpAmps if you don't know what this means or if you don't know why things are like this. The output of the filter can easily be determined by expressing the equality between the current through the capacitor C and the resistor R1 and the current through the resistor R2. If we call Z1 the impedance of C in series with R1, then Vin over Z1 is equal to minus V out over R2. The complex impedance Z1 tilde is just the sum of the resistor and the capacitor's impedances. The real impedance Z1 is then obtained by taking the modulus of the complex impedance. Now all we have to do is to substitute this impedance in the first equation, from which we deduce the expression of the filter's gain. This expression confirms that what we have is a high-pass filter, since the gain vanishes when the angular frequency omega is 0, and it increases as omega increases. The limit where omega goes to infinity gives us the expression for the maximum gain, R2 over R1. Now it is common to define the cutoff angular frequency omega 0 as the frequency for which the square gain is 1/2 of the maximum gain. I'll let you solve this equation, and you should find that omega 0 is simply 1 over R1C, so the linear cutoff frequency at 0 is 1 over 2 pi R1C. Since we still need to amplify the signal, we can choose here a maximum gain of 15, and since the majority of the muscle waves range from 5 Hz to 450 Hz, we can choose a cutoff frequency near the lower limit. So here I choose R1 equals 10 kilo ohms, R2 equals 150 kilo ohms, and C equals 2.2 microfarad, which results in a maximum gain of 15 and a cutoff frequency of about 7 Hz. This is perfectly fine, as the important thing is to get rid of the DC component without losing too much of the 5 Hz to 450 Hz frequencies. Now, using AC signals to control electronic devices is not simple. It is much more convenient to use DC signals. In order to perform the conversion AC to DC, it is common to use a diode bridge rectifier. However, in our case, this wouldn't work because our signal is probably still too weak to activate the diodes, which typically have a threshold of about 0.7 volts. The solution consists in using a precision full-wave rectifier. The idea is that when an op-amp is associated with a diode, it can behave like a superdiode, a diode with no threshold and with a zero resistance. Check my tutorial about op-amps in order to learn more about superdiodes. So here we have two op-amps that work in the linear regime, which implies that the inverting input of the first one is virtually grounded, and VB equals VC. If the input signal is positive, then the current going through R1 cannot go through R3 because D2 is reverse polarized. Indeed, with Vin positive, the only way that the inverting input of the first op-amp can be virtually grounded is if the op-amp outputs a negative potential. So the current coming from R1 can only go through R2. Thus, Vin over R1 equals minus Va over R2. And since no current flows through R3, Vc and Vb must be equal to 0. Now the current through R4 must be equal to the current through R5, so Va over R4 equals minus Vat over R5. By eliminating Va, we conclude that Vat is equal to R2 R5 divided by R1 R4 times Vin. Now, if Vin is negative, then the output of the first op-amp must be positive, as it is the only way to keep the inverting input virtually grounded. Thus, D1 is blocked and D2 is conducting. In this case, the current that flows through R1 can come from both R2 and R3. The equality of the currents coming and leaving the node at the inverting input is then expressed as Vin over R1 equals minus Va over R2 minus Vc over R3. We can use here the fact that R2 and R4 form a voltage divider, so that Va is equal to R2 over R2 plus R4 times Vb. If we substitute this expression into the first equation and use the fact that Vc equals Vb, we obtain an equation that involves only the input potential Vin and the unknown potential Vb. So we can solve for Vb and express it as a function of Vin. In a similar way, we can also notice that R2 plus R4 and R5 form a voltage divider, which is true only because the diode D1 is blocked. This gives us a second equation for Vb. So we can eliminate Vb, and this way we obtain the output potential as a function of the input potential. Now, if we choose the same value for the 5 resistors, then everything simplifies and the conclusion is that Vat is just equal to the absolute value of Vin. As a result, the signal is fully rectified as illustrated on the figures. In order to smooth out the output of the rectifier, we need to remove some high frequencies, so we use a low-pass filter. Taking advantage of the fact that the inverting input is virtually grounded, we can easily write the equality between the current through R1 and the current through R2 and C. If we call Z2 the parallel impedance of R2 and C, then we have Vin over R1 equals minus Vat over Z2. Here it is important for what follows to keep in mind that the output voltage is negative. The complex impedance Z2 tilde is easily expressed as the product of the individual impedances divided by that sum, so the real impedance Z2 is obtained by taking the modulus. By substituting this impedance in the first equation, we obtain the gain, which confirms that what we have is a low-pass filter. Indeed, it is easy to see that the gain decreases when the angular frequency omega increases. The maximum gain is obtained when omega is 0, thus Gmax equals R2 over R1. As for the high-pass filter, I'll let you check that the cutoff linear frequency F0 is given by 1 over 2 pi R2C. Here, we can arbitrarily choose a maximum gain of 1, and since we can hardly control our muscles in a time shorter than 0.1 second, we can choose a cutoff frequency of about 10 Hz. A possible choice for the components values is R1 equals R2 equals 82 kiloohms and C equals 220 nanofarad. These result in a maximum gain of 1 and a cutoff frequency of about 9 Hz. We need to perform a final amplification which, this time, is adjustable. This is a basic inverting amplifier. We can directly obtain the output as a function of the input by noticing that the previous low-pass filter reduces to this circuit if we remove the capacitor. The gain is therefore obtained by taking the limit of the low-pass filter's gain when omega equals 0. Therefore, V out equals minus R2 over R1 times V in. The presence of the minus sign is desirable since, remember, the positive output signal of the precision full-wave rectifier was inverted by the low-pass filter. For the components values, taking R1 equals 10 kiloohm and R2 equals 500 kiloohms adjustable results in a gain that varies from 0 to 50, allowing the output signal to reach the maximum voltage that can be delivered by the OpAmp. The offset selector is optional. It allows us to shift the output voltage up or down, depending on the requirements of the electronic device that we want to control. We have here a voltage follower, so the output Vout is just the voltage selected by the potentiometer. This voltage can be adjusted from the lowest potential to the highest potential of the power supply. If we opt for the offset selector, then we need a last difference amplifier. We can take the expression for the output potential that we found earlier. If we choose all resistors to be the same, then the output is simply the input minus the offset voltage. Since the offset voltage can be positive or negative, the output voltage can be shifted up or down. The last thing that we haven't discussed yet is the power supply. If you do some searches on the web, you will find many tutorials that propose EMG sensor circuits, but they all make use of symmetric power supply that requires two 9-volt batteries, which is not convenient. Moreover, one 9-volt battery is enough to achieve our purposes. The reason for the symmetric power supply is that OpAmps have their input and output voltages that vary around a reference potential that must be within the range of their supplied voltage. We cannot use a simple voltage divider in order to generate a reference potential because the reference voltage must have a low impedance. The solution that I propose is very simple. When we connect together the inverting and the non-inverting inputs of an OpAmp, it outputs a signal that is 1/2 of the supplied voltage. This voltage can serve as a reference provided that the output of the OpAmp has a very low impedance, which is the case for the LM386 OpAmp. Thus, with a single 9-volt battery, the LM386 outputs a voltage of 4.5 volts, which can be reinterpreted as the ground, while the positive and negative terminals of the battery are reinterpreted as plus and minus 4.5 volts. Here is the PCB layout that you can download from my website. Look in the description of this video for the links. This is a double-sided PCB, but since the top copper layer has only 5 connections, you can as well use a single-sided PCB and use straps for the top copper layer, which is what I actually did. This concludes this tutorial, and if you have any question or if there is anything that I didn't explain well, feel free to send me a message by using the contact form of my website. If you like this tutorial, please give it a thumb up, write a comment and share it on your social network. And if you feel generous, please consider making a donation. Thanks for watching.